We're going to talk about limited dependent variables, where our y variable takes value of just 0 or 1. It can be extended to cases where y takes on only some limited number of values, maybe 0, 1, 2, 3, but for now we'll stick with a simple case. Y takes a value of just 0 or 1. That can mean the y variable is answering some variety of yes-no questions. Now, one modeling strategy would just use OLS. Ignore the fact that it's going to predict values of y which might be greater than 1 or less than 0. And that's actually not a crazy idea. The basic linear model has lots of strengths. Mark Bellamy gives a good roundup. I put the link there. But there are other options as well. As so often the case, it's a trade-off. Other modeling methods called logit or probit can do this. These are two possible ways to bend the function so it asymptotes towards 1 as x get higher, but asymptotes towards 0 as x gets lower. Never actually crosses to be higher than 1, not lower than 0. It looks something more like CDF, the cumulative distribution function you may remember from way back when. The way we set this up, we say there's some probability of y being equal to 1, conditional on a set of x variables. We'll combine those x variables in the usual linear way that we understand. The function, which we'll generically label as f, can have some additional bends. Now this includes our standard OLS as a special case. That function's just the identity. Then we have OLS. But here we're going to twist it around and use a somewhat more complicated f function. The logit function looks a bit ugly. It's 1 over 1 plus e to the minus z. Then probit is going to be phi of z, where phi, that Greek letter there, is the cumulative distribution function of the standard normal. The graph there shows the PDF, not the CDF, but we should be all used to going between those now, the PDF of the logit and the probit functions. They look very similar. If you squint really hard, you might find some differences. Probit is the lighter one in that picture, a little more of the mass in the shoulders, a little lower right at the central point, and the tails are slightly different. In most situations, there's not a huge difference. And there is some computational complexity. The standard normal is a little bit more difficult for the computer to calculate, so logit functions get used a little bit more often. But that's a relic of the old days when computers were slower. Later we'll talk about different machine learning techniques that are a lot more even intensive to compute. In assessing how good are the different models, we have, unfortunately, more options available. We don't have that simple R-squared measure. Various measures of pseudo R-squared have been proposed, but they're often not very useful because they push the important questions into the background. Which miss is worse? Is it worse to predict yes when the true value is no, or to predict no when the true value is yes? Earlier we've used the terminology of false negative or false positive, type 1 versus type 2 errors. Yes, statisticians are really exciting people with fascinating names for these things. In general, we might not have a symmetric loss function that would penalize false positives and false negatives as equally bad. Remember back to our little happy face poopy chart there. The rows are whether an observation is predicted equal to 1 or 0, and the columns are whether that observation is actually 1 or actually 0. On the main diagonal, happy faces. Off diagonal, poop. You have to answer which poop is worse. Which of the bad outcomes is worse? Depending on what you're using the model for, they may be very different. If you're modeling, I don't know, whether it's worthwhile to show an advertisement to somebody online, well, you've been online, you've noticed that many of the ads do not fit you. But from the modeler's perspective, that's not a big loss. They've just wasted a little bit of your time, compared with the possible revenue gain from acquiring a new customer. In other cases, maybe some part of the national security apparatus is trying to figure out whether to go arrest somebody. They might have a different loss function if they get the wrong person. So, a subsidiary part of that is trying to figure out what predicted probability will be interpreted as y equals 1. Typically, the cutoff is 50%, but depending on the case and depending on the loss function, you might want a different cutoff. You can experiment with that. All right, so let's do this in R. First, we'll note this is the first, but not the last time when you'll see that you're learning about how to call the LM function, transfer over to lots of other. R uses the same basic syntax of how to specify a regression function in LM and GLM and maybe many others. The basic y twiddle x comes up lots and lots of other situations. So here, instead of LM parenthesis, we write GLM parenthesis. One extra letter. Generalized linear model. Then we distinguish logit and probit in the family part of the call, where binomial for logit or for probit family equals binomial link probit. It's kind of ugly, but either of these commands will give you a bunch of summary estimates that look incredibly similar to the simple linear regression output. You get coefficients and standard errors and t-stats and p-values, stars and all. Even the interpretation is actually very similar. You want to do t-tests on particular coefficient estimates, see if they're statistically different from 0, then exact same procedure. The interpretation is a little more complicated because the slope is going to be different for different values of the x variables. The function is not linear. Whether it's logit or probit, it's got that bendy kind of shape that I've sketched up there. Depending on the value of x, the change in the predicted value of y can be very different. For some people, this is just diminishing returns. If somebody's already got a whole bunch of other x variables that put them at a very high probability of some outcome, then adding a little more isn't going to do much. Going from 96% probability to 97% probability, doesn't move the needle. Whereas a change from 49% to 51%, that's a big difference. As earlier, when we discussed about how to interpret linear models with interactions, often the best way to understand is to choose some examples and work out the predicted probabilities. You can calculate how does a little change in the x variable change the calculated probability. In that graph at a point like x1, that probability doesn't change very much. That person has a low probability regardless. But x2, on the other hand, that point is where the slope is nearly at its maximum, so you'd see larger changes. It can be difficult to interpret all these coefficient estimates, but I've said to you before, you're now at the point where getting some results from R is pretty easy. The hard work is for you to understand and explain what it all means. I'll conclude with a bit of background. At the beginning of your journey, it's okay if you just think this is magic. It works even if you don't know why. But it's useful to begin to get a little bit of sense for what's behind that magic. When we did OLS, we were able to derive a convenient formula for finding the coefficient values that minimize the squared error. Remember, in ordinary least squares, the error term is y minus beta x. Sum those up, and having a nice formula makes things very easy. But if I didn't know the formula, I could find those estimates with enough computing power. A computer could just randomly pick numbers, find the ones that minimize the squared error term. You could just pick some numbers for beta, calculate the error, nudge around the value to see whether the errors get better or worse. Similarly, probit or logit is going to find some values of beta that minimize the new revised error term, which is y minus the function of beta x, where that function f is logit function or probit function. There are plenty of other estimators possible that just use a different function there for f. Whatever the function, have the computer find a beta value that minimizes that error. There's a good bit of work done in the background by people in computer science or mathematics to figure out what is the most efficient way of doing this search. In the old days, when computing power was really limited, efficient algorithms were really important. Although, even in modern cases, as computing power goes up, so too does the amount of data that we're working with. These problems are mostly solved for situations that you're going to deal with. What's going on in the background is what's called maximum likelihood estimation. Let me give a real simple example. If I see observations from a normal distribution, then the likelihood of seeing a particular value is the PDF. I can write that down for 2 observations. For now, keep the math easier, assuming sigma equals 1. So that's 1 over the square root of 2 pi times e to the minus 1/2 x squared minus mu squared. We deal with that exponent by taking the log. The log function is monotonic, so any value that minimizes the log of a function will also maximize the underlying function itself. Take the log, gives a bunch of constant terms that will drop out, minus 1/2 x minus mu squared. Then, as you remember from calculus, whenever you want to find a maximum value, take the derivative and set it equal to 0. Derivative with respect to mu is set equal to 0. With some algebra, we find the best estimate of mu is x1 plus x2 over 2, which, hey, that's exactly the average. Actually, if you go back in history, the normal distribution is sometimes called the Gaussian distribution because a mathematician named Gauss figured out this very property. With a little bit more math, you do the case for n observations and figure a formula similarly to estimate the standard deviation. Maximizing the likelihood of some probit or logit function is a bit more complicated, but people have derived the first and second derivatives, so finding the maximum value is quicker. But that's why when you look at the output, it will sometimes say something about how many steps it took to find the estimate. And on occasion, it might take a long time or it might not converge. There are various ways to try to solve that problem, maybe twiddling the convergence criteria, giving it more time. Its default is only make a small number of attempts and then give up. Sometimes you need to tell it to just run longer, try harder, but that's down the road.